Welcome to this explainer. We're going to dive right into demystifying the silent, ever-evolving infrastructure that powers our modern digital society. Whether you're making a quick phone call, joining a global video meeting, or streaming your favorite movie, every single one of those actions runs on an invisible backbone, a backbone working flawlessly in the background.
So, let's kick things off by asking a simple question. What actually happens when you hit send? We tap our screens all day without a second thought, right? But the journey your text message or your voice call takes is incredibly complex. It relies on technology that spans the entire globe and, increasingly, reaches all the way into space. To break this all down, our agenda for this explainer covers the digital backbone, how it works, telecom versus the internet, the wholesale network, regulation, and finally, the future of connectivity.
Section 1. The invisible digital backbone.
If we look at the word telecommunications itself, it actually tells a neat little story. You've got the Greek tele, meaning far off, and the Latin communicare, meaning to share. Literally, sharing information across a distance. But legally speaking, in the US, the definition is incredibly rigid. It basically means sending information across a network so that it arrives completely unchanged. You send something, it travels, and it arrives exactly as you intended. No alterations.
Now think about how wildly fast this has evolved. We had Samuel Morse's telegraph way back in 1837, but then it took nearly another 140 years to get the first mobile phone call in 1973. After that, the timeline completely compresses. Boom, the web in 91, the smartphone in 2007, and suddenly we're in the 2020s navigating 5G, fiber optics, and cloud platforms.
Section 2. How telecom actually works.
At its most fundamental level, every single telecom system relies on 3 lightning-fast steps. First, a transmitter converts your info, like your voice, into an electronic signal. Second, a transmission medium carries that signal. This could be a physical copper wire, a fiber optic cable firing pulses of light, or even invisible radio frequencies. Third, a receiver picks up that signal and converts it right back into your voice at the destination. And all of this happens in literal milliseconds for every single connection.
So how do those signals actually find their way? Well, we've seen a massive shift in data routing over the years. We moved away from traditional circuit switching. That's where a dedicated continuous path was reserved for your entire phone call. Sure, it was reliable, but it was highly inefficient because it reserved the line even when you were completely silent. Now, we use packet switching. Think of it like this. Instead of holding a whole highway open for just one car, packet switching breaks your data down, sends it in tiny, independent pieces, and then reassembles it at the destination. This highly scalable method is exactly how the internet and modern voice-over IP systems manage massive amounts of data without wasting space.
But, of course, packet switching requires rules. Think of protocols as the agreed-upon languages of the network. You've got SIP, which sets up your voice and video calls, SS7 handles legacy routing and SMS, and then RTP is the heavy lifter. It carries the actual audio and video content. Every modern network relies entirely on these specific languages to function.
Section 3. Telecom versus the internet.
This is a super common point of confusion, but the distinction is absolutely vital. Put simply, telecom is the physical road system, and the internet is the cargo traveling on those roads. Telecom is a much broader category. It's over 150 years old, encompasses TV, radio, and mobile, and man, is it heavily regulated. The internet, on the other hand, is built on top of that infrastructure using TCP/IP. It's run by ISPs and content delivery networks, and historically, it's seen much lighter regulation. And you're interacting with both sides of this constantly, right? You've got wired networks, like those fiber optic cables offering ultra-high speed and stability, though they obviously require physical infrastructure. And then you have wireless networks, radio, 5G, Wi-Fi, satellites. These give you mobility and coverage, even in the most remote areas. These networks scale all the way from the local area network in your home straight up to the world's largest wide area network, the internet itself.
Section 4. The wholesale network layer.
All right, let's zoom out from your personal smartphone. Most of us only really think about consumer telecom, like our personal mobile plan or home broadband. But when you make an international call, your local carrier probably doesn't own the network in the country you're calling. Instead, they rely on wholesale telecom. This is a massive, invisible global layer where carriers trade millions of minutes, routes, and network capacity at scale across borders just to connect you.
For a business launching voice services, they have to tap into key wholesale tools. They use wholesale VoIP termination to route massive call volumes globally. or Cloud IMS, which delivers complex media over IP without them having to buy a single piece of expensive physical hardware. Throw in soft switch rental and SIP trunking, and these are the exact things that dictate a company's call quality, their costs, and their overall operational resilience. Let's do a quick jargon buster here. MVNO, that's a company selling you mobile service while actually leasing the physical towers from a bigger host carrier. QoS, or quality of service, prioritizes your voice traffic so you don't lag during a call. CDRs are the call detail records, vital data files for billing those wholesale minutes. And edge computing is this massive trend to processing data closer to the source rather than in some distant cloud, which absolutely kills latency.
Section 5. Regulation and net neutrality.
Because reliable communication is so tied to national security and economic growth, telecom is arguably one of the most heavily regulated industries on Earth. Governments literally auction off invisible radio frequencies, that's spectrum allocation, for billions of dollars. They enforce interconnection rules to force competing networks to connect, mandate universal service so rural areas aren't left in the dark, and rigorously enforce strict consumer protection standards.
Within this regulatory space, the undisputed heavy hitter is net neutrality. This is the contested principle that internet service providers must treat all traffic equally. Basically, they can't artificially slow down or prioritize certain websites. The sources we're looking at show that supporters see this as absolutely vital for fair competition, ensuring startups can reach users just as easily as the giant tech monopolies. On the flip side, opponents argue these rules limit an operator's ability to manage their own networks and recover the massive investments needed to build all that physical infrastructure. It's a highly active debate, and honestly, the rules vary wildly depending on which country you're in.
Section 6. The future of connectivity.
The telecom industry is currently undergoing a structural shift that's honestly just as massive as the jump from analog to digital in the 90s. As we look at trends for 2026, the industry is ditching bulky, proprietary hardware. Instead, they're moving towards software-defined networks, or SDNs, and cloud-native infrastructure, making things like 5G network slicing possible. Combine that with artificial intelligence driving predictive network maintenance, and you have networks that can instantly deploy services and fix themselves before you even notice a drop in quality.
Looking further ahead to the 2030s, the landscape shifts entirely. We're talking active research into 6G, which promises terabit per second speeds and sub-millisecond latency. Pretty wild. Open RAN is allowing operators to mix and match hardware from multiple vendors. Low Earth orbit satellites like Starlink are blanketing previously unreachable areas with broadband. You've got billions of IoT devices scaling machine-to-machine connections and quantum communication promising theoretically unbreakable encryption. To survive all this, operators simply have to adopt totally flexible, software-defined platforms that can adapt without needing wholesale hardware replacements.
Which brings us to our final thought. From the basic electronic pulses of the 1800s to the quantum satellite networks of tomorrow, this invisible backbone powers our hospitals, our financial markets, and our daily lives. As quantum encryption and 6G completely reshape our reality, ask yourself, if this silent infrastructure went dark tomorrow, how long would society actually function? Keep exploring, and thanks for joining us for this explainer.